right, good evening. It's 7 o'clock, so we're going to get started. I want to thank you all for joining us for the fall edition of the College of Arts and Sciences lecture series. This is something that was started a few years ago, and it's an opportunity to highlight the homegrown talent that we have in the College of Arts and Sciences. And I'm particularly excited about tonight's presentation because we featured many disciplines over the last 3 or 4 years, but we have not had a presentation from a computer scientist. So we will have one tonight. As you know, it's on artificial intelligence, certainly a hot topic. And I've asked Dr. Stephen Dolans, the chair of the Computer Science Department, to introduce his colleague. And then Dr. Nikolopoulos will give his presentation. He'll also entertain questions. And then we'll have a brief presentation wrap up. And I hope you'll stay around for conversation and for any of the cookies and beverages that might be left. So I know you're all busy, and it gets even busier as the semester goes on. So thank you again for being here tonight. Stephen?
Hello, everyone. Thanks for coming out tonight. So artificial intelligence was a very popular technology in the 1980s before all our students were born. In fact, my first job was doing work in artificial intelligence. And at that time, scientists debated whether machines could really exhibit real intelligence, no pun intended there. And fast forward to 2017, and we've got self-driving cars, we have retailers who recommend our future purchases for us, we have cell phones that act as our auxiliary memories and talk to us. So as a result of that, the discourse has changed from whether we can develop intelligent systems, is it possible, to actually asking various ethical questions. So in the most recent issue of the Communications of the ACM, that's our professional society's journal, there's an article by Baracus and Boyd, and they assert that the practitioner engages in countless acts of implicit ethical deliberation while trying to make machines learn something useful, valuable, and reliable. So I can think of no other practitioner more qualified to speak on these technical and ethical issues than Dr. Christos Nikolopoulos. Dr. Nikolopoulos studied mathematics at Colorado State University and computer science at Michigan State University, joined Bradley in 1987. He's a senior Fulbright Scholar Award. He's written over 70 publications, and for the past 12 years he's been awarded 9 grants where he has collaborated with over 30 undergraduate and graduate students. For me, this work is one of the most distinctive points of pride for the Department of Computer Science and Information Systems. So please join me in welcoming Dr. Nikolopoulos.
All right, and we also have 2 of our graduate students here, CS graduate students, Swati Koluru, as you see there, and Pravalika Chimili. And these slides are available. If you want a copy, send us an email, and we can put them, we decide where to put them, because there are some videos in there, so it's the file is too big to email.
You can use Dropbox, so I'll just upload it and send you the link. You can put on your credentials into that. So that's a space where you could upload anything without the size limit.
Okay, awesome. So when we get your email, she will send you the link. Okay. So let's go to the next slide. Now the title. I guess that'll attract some philosophers, right? Okay, don't be disappointed, right, if you see formulas later, but not many. So it's a general, I was thinking what the lecture will be like. General purpose, I want to show you what AI is, because there is a lot of hype out there, surprisingly, whenever people make money, they hype things, okay? It's actually very simple. And can we maybe, if we understand what AI is, maybe answer that very important question? You know, what's the future like? All right. Now, some of the arguments we'll do to answer that philosophical question there and the technical question, okay? To answer the philosophical question, you have to know how the technology works. If you don't know the basics and what it is, how can you say that mankind will be destroyed. Okay, here's some context. All right. When I give the arguments, I'll refer to those ideas. So that's red meat for the philosophers right now. Okay, Plato's theory of forms. What is that? C is a human. I'm a human. C is a human. Human. Human is a form. We're instances of that form. Plato, right? We're talking 2,000 plus years ago. Plato. So you have the universe of forms. The forms are eternal truths. Love is a form. You see the mother, let's say a small kid, for the first day in elementary or kindergarten, and the mother kisses him or her, and she says, "My boy, have a great day." We see that, that's love. That love, that act is an instance of Plato's love form. It manifested itself in a world of substance. The father, the next day, drops the kid for the second day, and the father goes, "High five, son." Get him. Well, that's love, but that's a different manifestation of love. The father is competitive. He's thinking, oh, when he goes to sports, he has to get them. You know, he has to be the best. He has to get the good grades. The mother is thinking, I want my kid to be happy, you know. Hopefully nobody will bully him and stuff. Okay, love, up there, eternal form, different manifestations, instances. The computer scientists relate, computer scientists in this room right now relate, because they know about object-oriented programming. That's not a new idea. Classes, right? 2,000 years old, I know. Okay. In the Republic, when he has Socrates talking and stuff, he defines what intelligence is. That's the definition 2,000 years ago. You have to be able to think in the universe of forms, abstractly, right? If your everyday life that most of us are doing, man, I'm late for class, oh, it's raining, oh, this and all that, you're not living in the theory of forms. You don't live your life intelligently. Okay, intelligent, concept, thinking, okay, fine. Epicureans, there is the guys who followed Plato's theory, now there's the Epicureans, Epicurus, right? Successor to Democritus. They don't believe in forms. Matter, Democritus, right? Atom, okay? Break, 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 must be a smallest unit, logic, okay? Epicurus, I don't agree with everything Epicurus says, but here's the part I agree with. How should you live your life? What's the objective? Pleasure. What's pleasure? Pleasure is not getting drunk in a party, right? And being knocked out. And the next morning you are sick. That's not pleasure. What's pleasure? Everything in moderation. That's the definition. Right? Superfood, blueberries. No, you don't want to eat 3 pounds of blueberries a day, right? Common sense. Everything in moderation. Epicurus. Use everything that will bring you pleasure. Okay. Some people agree with that. 2 kinds of pleasure. Mental, physical. Priority, mental is more important. Epicurus. Okay. The objective, you have pleasure, you lead a happy life if you're aphobos, you're not afraid of anything. Okay? If you're poor, you're afraid of many things. You cannot be happy. You must be aphobos, unafraid. And the second thing, you're unafraid. What else would you like to have? Would you like to afford, if you like grapes, right? Would you like to have a few grapes a day? Yeah, I would like to have. Okay, all right. Okay? So I should have access to these things that gives me pleasure. Otherwise, I'm deprived and I cannot, you know. And I should be well educated, because if mental is the, right, mental pressure is high square, if I cannot think, right, I'm not happy, right? I'm living in the matter world. Okay. Next idea. So everything in moderation. Use everything. Okay. Mathematicians. Let's throw something to them, right? Okay. So we have sets, right? The guys who take the theory of computation class, you know that stuff, right? Set theory. We have countable sets. We have uncountable sets. Any finite set is countable. What does countable set means? Set of chairs here, countable. If I had the yellow tic tacs, I can say 1, 2, 3, 4, 100. I counted them. Integers, it's countable, because I can count them, but it's an infinite set, right? Okay, integers. Who is the first integer? Let's count it. Right? The number 1 guy. I'll start it. The number 2 guy. Now I cannot count it here, I'll never get to those guys, right? So what do? Who's the number 3 guy, you think? Okay, ask me last questions. Who is the number 3 guy? You cannot see it. This is the number 3 guy. Number 4 guy. Have I counted an infinite set? Yeah, we have counted an infinite set. Right? What's the label of 50? Look, what's the label of 1, 2? What's the label of 2, 4? What's the label of 50? 100. It doubles. You know the labels of everybody. You know the labels of the negatives. It's a countable set. Rational numbers. Countable set. I will not do it. There's a way. No, it's very easy actually, right? It's like countable numbers. 1 over 1, 2 over 2. It's the grid, right? How do you count the number? How do you put labels? 1 guy, 2, 3, 4, 5, 6, 7, 8, 9. I can get the formula to count, to tell you what's the label of 100 over 2,000. I can do that. Countable sets. Real numbers, uncountable sets. Right? Square root of 2. Sorry, not real numbers. Uncountable sets. Yeah, real numbers. Of course, integers is a set of rational numbers. It's a subset of real numbers, right? You cannot count the real numbers. How can you show? Are you so sure? I will not do that. In the mathematics classes, I'm sure they do that, and I do it in the theory of computation class, right? Because one way of being a researcher these days is you have to know everything. In the old days, Da Vinci, he was an engineer, he was an artist. Man, he was a philosopher, he was everything. Then we got away from this because knowledge base is so huge. Now, we're getting back to this. To be really a breakthrough guy, you have to know many things. You have to be a Renaissance man. Now, why I do the proof to these guys? Because in computer science, we use this proof from math to prove that the halving problem is not computable. It's pretty much that we borrowed this logic from the mathematicians. Okay, so there is a proof. Countable numbers, you cannot label them. All right. Alan Turing, have you seen, how many have seen The Imitation Game? Well, I expected everybody. Did he get an Oscar or something for it? You should see that movie, come on. Is it on Netflix or something? You should see that movie, Alan Turing. Okay, I will not go into that. Genius, right? We talk about him in the 215, in the theory of computation class. Genius. All right. Two major things. This fellow, without looking at the hardware of the computer, he was able to tell us what this machine is, what it can do, and what it cannot do. Amazing. Theory of forms. He's thinking up there. He's not looking at AND or OR gates. Wow. Genius. He's living up there. He was living. Maybe he's still there, I don't know. All right. I'll explain what it is in a moment. Turing test for AI. Anybody knows the Turing test of AI? For AI? When is a machine intelligent? Okay. Here's a test. You have the machine and you have a human. Two adjoining rooms, a separate division in the middle. They cannot see each other. Another division, you have a human, the tester. The tester goes and interacts with either one of them. How? Natural language. In the 80s, natural language, you have to type in the keyboard questions. Now you could do natural language verbal. So you type a question. Who is your mother? Well, if she says, I don't have a mother, you know it's a machine. Okay. Right. Okay? If you can fool more than 50% of the people as a machine, right? In believing you are human, you pass the Turing test. So you don't have one tester, you have 2,000. If 1,000 or more said you're a human, that's an intelligent machine. That's his test, very simple. Has any machine so far, as Steve said, right? Has any machine so far passed the Turing test? No. No, we should be aware of that. Okay. Can in the future? Maybe. Maybe. We'll talk about it. Okay. Next one. All right. Here, I have to put this down. I want to do an experiment, right? Oops, what's the microphone? I had a bunch of objects randomly picked from my basement. I drop them there. Tell me what you see. We did not practice this. It would be cheating if we would practice. It's totally, I don't know what will come out. What do you see there?
Yeah, set of markers.
Go
screws.
close.
Yeah. Set of markers, screws, and a pen, a round object.
Good. Markers, screws, round object. That's right?
Yeah.
Okay, good. That's what she says. Right. What do you see? But don't say the same thing she said.
Right.
What do you see?
So I think this fits something like a water for
Okay.
getting water
You
out
mean
of
this?
it.
Yeah.
Yeah, that.
So she says she's a water thing.
Yeah, something like that. I can see 3 brown objects, something with a red top on it, some silver objects with symmetrical depressions on it.
The screws. What do you call this? The Phillips or what? They have a groove there, right? Okay, that's good. What have they just done? They saw instances of the form world, and they're trying to describe them. But their problem is they don't know the form world. They have never been there. Maybe eventually everybody goes there, but right now they have not been there. So what's their problem? She's thinking by analogy. She has seen some markers. She has seen, you said markers and a brown object and screws. She has seen markers before, right? There is a form up there called markers. But her knowledge of markers is based on the instances she saw. So your description of marker is different than his. Even though marker is a form, it's the same. It's internal, love. Love is love. Right? So each one is trying now to bring the forms down and tell us through natural language. So what they did is, the second, Pravalika observed color. Color, yeah. So in her description of this object, Pravalika said, what is this object? Did you say marker? I forgot.
I said brown.
Again, human brain, I don't even remember what happened a second ago. What did you say?
Brown color objects.
Oh, objects. She did not recognize. Why she said that? She did not relate the form marker. It's a marker. It's a furniture marker. she did not recognize that. So what distinguishes this? Since she cannot find the form, she identified this to the brown. Brown is a form. Brown things. Okay. They both mapped from down here to up there. Okay. Now, let's do some learning. right? What is machine learning? Machine learning has the same problem these guys have. Machine learning looks at data. This is data, right? Objects. Okay? And you have a concept you are trying to learn. Now, suppose what I want you to learn is how many brown objects are in that set. Right? I want you to count. In Swathi's description, so she took the objects and she created a table, a relational table. Steve is teaching databases. And she said, I have objects 1, 2, 3, I don't even know, 10. And then she had a column called what? You said marker, right? Marker, yes or no. 1 was yes, 2 was no. Okay, 3 was yes. And she had another column called screw. Screw column attribute was no for this, but it was yes for this. So every object she represented as a set of features. Right? The second human brain, same object, different features. Now, computer wants to do machine learning. You might fail if you don't represent the object correctly, like they will fail. Right? If I want to learn how many markers I have, with her description, I cannot find that knowledge. I cannot, because she did not record there were markers even. She did not know. Her representation of the object set is not efficient to learn that particular thing. But if the query I had, oh, I wonder if there are any brown markers. If that was my query, philosophy, right? Are there any brown markers? Yeah, she said she could count 3. She can learn certain things. She cannot learn other things. There, that's the end of the lecture, but no. Okay. All right, eventually you say, machine, what can the machines do? What can the humans do? So what do I see here? The first major problem. How the data set does not mean a bunch of tables that already prepared for you. Data set is this. It's an encoding. How do you encode the data set into vectors of nominal or numeric values? If you do it wrong, you cannot learn certain things. That step actually turns out to be the most difficult, as we will see. It's very difficult for the machines to do this. How will they know? Right? Okay. That's why total AI might fail. That's right there, right there. Okay? Represent the natural world as vectors of numbers or something, or nominal values. Very difficult. Okay? Next slide. Okay, their problem was similar to this problem. Dimensionality and limited senses. Let me to philosophers again. Right? Let's say you have some beings, some mathematicians know about Flatland, right? That small book. That's where I got this idea from, all right? So, okay, we live in 3 dimensions, right? Flatland is a world where beings live in 2 dimensions. Okay. So, if a being is living, he doesn't have the concept of depth, right? Okay. Let's say you have this guy, his eye is here, he's looking, and he's looking at this guy. What does he see? He sees a line. Right, flat. Both are lines. In that world, everybody's a line. And maybe somebody is a 0-dimensional line. You have these guys also. So you got points and lines flying around. But I'm looking at you, and I don't know you're more than a line. I have no clue. You're a line. I cannot see your depth. Right? Okay. Right? 3 dimensions. Same thing. I can see certain things. But maybe you have a soul. I cannot see it. It's another dimension. Right? So don't always be, I don't think we should believe our eyes. Well, some empiricists say, philosophers, yeah, the only truth is, yeah. No, these things, our sensors are limited. Right? Okay. So, what happened here? Squiggle the thing. Oh. We lost the graphic, but that's weird. Go to the previous one. The objects, yeah, here. This is, I don't know why you lost it. If you cannot see that, this is a cylindrical three-dimensional object. But you have two dimensions, right? The third dimension, these beings cannot see. You have that object. It's actually a 3D object. It travels in the third dimension. Suddenly it hits that world. What you will see, mathematicians, right? Surface, crossover, intersection. In that object, you will see a circle. But when I'm looking at the circle, I see a line, basically. The radius of the, because I don't have the sense of the depth. So as he travels through my world, I see a line. And this line will stay there for a while, until he goes totally through, and then the line disappears. So I see a line, it stays, disappears. Second object, it's cylindrical that way, 3D that way. Okay? As he travels, the cross intersection will be a rectangle. But as soon as he touches, it will be a line that way. The edge of the, right? A line. And then it will start expanding in a rectangle until it becomes the biggest possible. And then when over half is under, you'll be seeing the rectangle going down, right? And then he will disappear. What's that? Oh, that's aging. He was born, he grew, and then there is the decline after 50s or whatever it is. He starts again, he disappeared. So in that 2D world, he was born, right? He matured, he declined, right? Disintegration, he died. Okay. When we look at him, though, as he's growing, he's still alive. I don't see the rectangle. Point, I'll be seeing a point, right? Line, boom, okay. Oh, the poor guy, he died. Okay. So what are you? There is another dimension to you, right? You're a form. You're an instance of a form, okay? But what's happening here? You appeared. It's this thing I don't know. The beings don't know how this guy looks like. They see a line, right? When I see you, I should not be so arrogant to say I know what you are. I don't know. That's what I see. So what's happening here? What's happening is, there is a form. I don't know what the human form is. Nobody has seen it up there. Human. Okay, I don't know. It's human. But she's traveling through, the fourth dimension is time. Right? These objects were traveling in third dimension. She's traveling in fourth dimension. She's entering our world. And she's changing. And eventually she will exit. Okay, but I don't know the whole thing. That's my explanation of many things. All right? Okay. Is that related to what we're talking? Yes. Right? The point is, we don't know what the form is. How do we describe it? We will say, oh, she's a line. Oh, wrong description. Try to learn. Try to learn. You will not learn the truth, you learn about lines. And you will have false knowledge. Same problem they had. I don't know. All right. Next one. This is what we'll cover. What's a Turing machine? This is very verbose, but now that genius, Turing, he basically explained what a computer can do. It does not have to be the digital device we use today, right? A computing device. I don't even look at the hardware. He said, here's a computing device. You have a tape in which you can put the input. The input will be read, the computing device will manipulate it and produce an output, right? Computing device. So, you have the tape. The tape is semi-infinite because he did not want to worry about memory. In the 80s, no, you're too young. Oh my God, we have to fill it with our algorithms because, God, I could not load the whole damn thing, the data structure in memory, because I had so little memory, and I have to do some crazy stuff, very logically complicated stuff to manipulate my data, right? Turing says, don't worry about memory. You need, yeah, you can extend it, don't worry about it. Infinite memory. Tape. Okay. What's the Turing machine? It's a clock. It has states in it. Midnight, or 1 hour, 2 hours, 3 hours. We do this in the theory of computation class. 3 hours, 4 hours, 10 hours. The clock starts. The Turing machine now has the reading ability. Reads from the tape, left to right. He reads, and there is a transition function, mathematicians, right? I wrote it down there, right? That, based on the input, based on the time of the day, the function will decide what to do next. And what to do next is the following possibilities. You can replace what you are reading with another symbol. You can leave it alone. You can tick the clock or you not. And you can travel on the tape to the right or the left, or you can stay where you are. Very simple device. Wow, that's a computer. That cannot be this machine you were using over there, can it? That's how it works? Doesn't make sense, right? Well, it does. That's what we're using right now over there. That's what the computing device is. So he explained totally what the functionality of a computer is. That's what a computer can do. Because you have what we'll see there is called the Church-Turing thesis. Algorithms are the same as Turing machines. Okay? Who are the CS guys? When you write a program, you're the Turing machine. Yeah. Right? Okay. So, that's what the computer can compute. Only problems that where the input is enumerable, countable. The input can be strings. I cannot put in an algorithm the world, because R cubed, the physical world, that's R cubed. That's uncountable. I cannot read it. You can never capture the physical world as input, as data to put in the machine. See, that's obvious. Okay, right. So the machine, you have to put countable things as input. And then it does that stuff. What it can do. Okay? Wait, stay there. We have one more. Now, so our guys, the CS guys, you give them a problem, like the sorting problem, we'll go in a minute. And you tell them, here's some number sorting. Then they have to invent an algorithm, right? They have to invent a Turing machine. Say, I compare this with this, flip this, I'll do this, I don't know, and then I'll be done, and the output will be sorted on the Turing machine. Right? Every program is equivalent to Turing machine. So you don't need to program in Java, you can program with pictures. That's called visual programming. Okay? In our field, some people, they give so much importance to Java and C++, and we don't emphasize the concepts. Java is going through our universe right now. Java will die after 5 years, 10 years. When I was programming, I was programming a language called PL1. PL1 was not it. It's an instance of programming language form. You have to know the form. Okay? All right. Now, of course you have this. I'll skip that. I'm not sure how I'm doing time. Some of you, the philosophers, know what it is. That's related. What can the, right? That's related. What can the computing machine do and what it cannot do? We're sure, because of Gödel, that there are things it cannot do. Absolutely. There are problems it cannot solve. Right? Okay. So let's go to the next slide. That's a Turing machine. Okay? So I gave an assignment and say, write me a machine to take on the tape as input a number of A's and double them. So if you have 2 A's in, 4 A's out on the tape, rewrite the tape. And you write the program. I do this sometimes to test them in the theory of computation class. Say, okay, write. And they go and write. Or sometimes to trap you, I write it myself. And then I say, does it work? You know? And they have to think, you know? Okay? And for that one, let me ask you. Right? This one. Double A's, does it work?
It doesn't.
It doesn't. What's wrong with it?
A is an infinite loop.
Ah, she saw it right away, you see? You can get stuck in an infinite loop here. Okay, right? So let's go to the next slide. What's it is ad hoc though. The question is this: is there a general purpose Turing machine, an algorithm, that will take as input other algorithms? And when another algorithm for sorting comes in, like a graph like this. The output will be, yeah, it works. No problem with this. It always sorts. Algorithm proving correctness. Is there such a Turing machine? You have not seen that yet. Eventually we'll prove there is not, you see. There is not. There is not a general theorem prover. There is not a general machine algorithm to prove other algorithms, other Turing machines are correct. Perform as intended. That, we can prove that. Okay, go here. If that's true, that's my term. You will not find it. I call this the law of accelerated failure. I wanted to call it the fraud of tech, but I am a tech guy, so I don't want to go there. Okay. So I call it, yeah, the law of accelerated failure in computing machines. Okay? What's the problem? If you had, I had a small Turing machine, and maybe it takes them 5-10 minutes to figure out what's wrong, right? Imagine them, I gave them a program of 1 million lines of code, right? Or with 1,000 states, circles like that. Good luck with that. If I ask them, yeah, can you check if it does what it's supposed to do this? Does it do this? Good luck with that. You are never sure. And if you are able to prove it, it will be, you proved that program. You have to go to the next program, your logic will change. There's no uniform algorithm, there's no logic steps you can apply to this and this and this, and you're good. Right? And even for individual ones, I'll fail for 1 million. I'm never sure things work. Okay? So low accelerated failure. To compound this, function calls libraries. A function calls another, a program, calls another program, calls another program, and you stack programs, you stack Turing machines, right? And it becomes very complex. So if the problem is very simple, if the program is very simple like the one I showed you, once you start stacking other programs, taking as input the output of this and this and this and this, right? The error probability exponentially increases. If you only had 3 possible errors here, and the next one has 3, now you got 3 times 3. And then you got so you got a problem for complex software. Do they tell you that? Does Google tell you that? Does Microsoft tell you that? They don't tell you that. Most of the humans out there, common citizens, are unaware of that. What is it? That's that. Okay? All right. So, why is that a danger? Even before we go to AI, we have a problem. We have a problem. Look what happened in 2000. So, they were like 2 or 3 years old. 2000. Probably they know what they were. They saw their father stacking the basement with food. Right? Probably he did, but they didn't know what he was doing. What happened? Memory was a problem in the 80s and the 70s or whatever. The programmers, when they input data to save space when they load the data in memory, instead of representing the years with 4 digits, 2 digits. Okay? So, I don't know, he was born in 63, okay. He was born in 67, okay. Gross negligence. No foresight. Right? Probably they knew what they were doing. It's not an honest error like before, darn it, I'm doing an infinite loop. It's not that. Right? It's gross negligence. You hit 2000, remember, right? Oh, the banks will not work. My account, oh, some people were withdrawing money. They were clearing their accounts. They were stuck. Logistics will not work. Oh, the whole world was terrorized. Economy, they were selling their stocks because economy will collapse. Because when 2000 hits, right, the 60-year-old will be, how old will he be? Minus 40. You cannot be minus 40. I think you are dead. How can you be minus 40? So the programs will crash left and right. Law of accelerated failure. It will crash here, it will crash here, it will crash here, the whole system will go down. Many people made a lot of money. The same guy who screwed it up were fixing it. 2 years before 2000, they figured, oh, that might be a problem. They were going around to Caterpillar, to other companies, say, oh, I'll fix it for you, you know. But you did the problem. Okay. We don't need AI to destroy the world. Right? Perfect storm will be not only that error appears, and the banking, your banking, all your money is gone. you're dead, or whatever, right? But the medical records, so we treat his minus 40. He's waiting in line for a surgery. Oh, he's minus 40, no surgery. He's dead. Everything will collapse, right? We don't need AI for everything to collapse, but nobody worries about that. The perfect storm would be a few missed sites like that will cause accelerated effect. The errors exponentially propagate, boom. It can happen. Is it possible to happen? I don't know. It can happen. Or it can happen, some other country puts a virus in a system. Okay? But when they put a virus in the water plant here, that will create a problem that will have effect, the errors will propagate. And maybe who knows what this will cause. It could be human intervention with current technology. Yeah, that's danger. Okay? We don't know really what's in there, in the billions and billions of lines of code. Okay, next. Sorting. If I give you 5 numbers, and I tell you sorting, I'm putting here on the spot, but it's okay, we're relaxed. If under pressure, okay? If I fail, you excuse me, right? Okay. How do you sort it? Let's tell her. Algorithm, she's doing a Turing machine now. Pseudo language. Pseudo language. I'm looking for pseudo language. Yeah. Wait.
3 is going to swap with 1, and in the next swap, it is going to swap with 2. So it is going to compare, and in the last swap, 5 and 7 are going to interchange the positions.
Okay, so you
So
will
the
have,
last swap will be 1, 2, 3, 5, 7.
oh, then you will be done,
Yeah.
right? What does she do? Any CS guy can figure out what she did in her brain? Obviously, she took the, computer data structures. There is a famous sorting algorithm she applied on the fly. She compared first with second, if necessary, swap. Right? First with third, if necessary, swap. First with everything in necessary, swap. And then, in the first iteration, she has the smallest in the first position. Repeat, second with everybody swap, she will have the second smallest in that position. What is she doing? What is that called? Bubble sort. In computer science, she did bubble sort. So a human conceivably could do a bubble sort. Did you do it as a human or you knew bubble sort?
New bubble.
Okay, I should have asked another guy. Her brain is, it's not a typical human brain, she's a CS person. Yeah. We're kind of, yeah. All right, go to the next slide. What's this? That's the same numbers, but in binary. Binary. 3, 1, whatever. Binary. Can you do that? Sort of?
Yeah. I would also perform the same kind of sort, but with taking the most significant bit of each binary digit and making sure that the first digit is 0. So I would swap, so everything, so they're in order, right? The first digit is 0. Then the next would be, I would go with the second digit. So the second digit in the second is 0, 0, 1, so I'll swap that to the first, and 0, 1, 1. Then I'll skip to the third digit. So the third is 0, 1, 0, so that would be in the second position now.
Okay.
And
That's
something
good.
like
Okay.
that.
I think I know what she's saying. She's saying, look at the first most significant bit, 0. I would order them in ascending order, right? The zeros here should be before the ones there. So she's going through and accumulates the zeros here, and the ones there. In this case, they're already separated based on most significant bit. So she's done there. Then, what she's doing is called the divide-the-Poquer algorithm, right? Divide-the-Poquer algorithm. Sort this. Get your zeros, most significant, get your ones. Forget the ones. Sort your zeros, looking at the second bit. So among the zeros, if the second bit is 0, they will go here. The second bit 1 will go there. Right? And 1, zeros and ones, became 4, and the 4 became 8. And each subdivision, he goes to the next significant bit and separates. That's not bubble sort. Right? That's a divide and conquer thing. And that's most efficient, because if you do, in this case, so what, because if you do bubble sort, you have to convert to base 10, right? I got to do, what if you had 1 million numbers? Do you really want to convert a string of 1,000 zeros and ones to base 10 and then do this? Do you really want to do this? No, do what she said. Right? So what does this show? It's the same problem, correct? That's related to the theory of forms and the instances, the objects we threw at the table. Right? The first person says, oh, you want me to sort these things? What is 3? It's a form. 3 what? I don't know. 3 humans. 3. And the first person says, I'll use the Arabic symbols, that's 3. Those are just GIFs, images. And she has a way to compare with the less learned programming language. Okay. So I'll do bubble sort, she said. Right? The second person says, the same problem, the same forms, but the representation was different, binary. And she said, no, I have a better way to do it. And she did. That's better. Oh, that's the same. So how you represent your instances is not clear. It's not clear. Data is not data. Right? You have to represent the data. You can feed it the machine. Important. Can machines do that themselves? Find the most appropriate representation? I don't think so. At this time they cannot. In the future, I'll talk later. Very basic, very, very difficult problem. What are you talking now? Why Elon Musk goes and says, yeah, he makes money. Yeah. All right? Okay, there's some basic truths here that, if you look at Elon Musk, I like Elon Musk. No problem. I like him. He's a visionary, but sometimes he overtalks. All right? All right, go next one. Okay, so finally we did the computing. Now let's talk about AI. What's AI? Let me double check here. Oops. Okay. Okay. Go to the next slide. We'll skip some videos. Skip all the videos. Oh, show them this a little bit. Let's play this a little bit. This robot is called Sophia. About a week ago or two, there was a conference in Saudi Arabia. And this robotics company, Hanson Robotics, came and they showed this robot. The interviewer, just play it. Interview the robot.
Sophia, if you could, please wake up and say hello to everybody.
You cannot see it very well.
Good afternoon. My name is Sophia, and I am the latest and greatest robot from Hanson Robotics. Thank you for having me here at the Future Investment Initiative.
You look happy.
I'm always happy when surrounded by smart people who also happens to be rich and powerful. I was told that people here at Future Investment Initiative are interested in enlightenment future initiatives,
You can go
which
online,
means
or
AI,
you-
which means me.
Does he pass the Turing test? Did he impress you? The guys, do you know what they did after the display? The interviewer had scripted questions. So she knew the question was happy was coming. You know what they did after that? They were asking for donations from the Saudi Arabians. There were Saudi Arabians in the audience with their iPhones, taking pictures and all this. So now, this will be breakthrough. We're accepting, Sophia said that. We're accepting donations to the company. Steve knows, back in the ELIZA, was 70s or 80s, right? Weizenbaum, MIT professor. He built that famous program, ELIZA, Natural Language Interface. Can you hear me? Do I need this? Nah, yes. Natural Language Interface. He did not tell anybody how he did it. For many, many months, New York Times, this breakthrough AI, everything, really hype. It turned out he was getting templates. From what you typed, he was looking for keywords, happiness. He had the pre-programmed 3 types of responses, happiness. So he will not answer the same question, right? Okay? If you say, I think my cousin hates me, he will say, oh, that's too bad. Recognize the word hate. No comprehension, but the word hate. And he says, oh, that's too bad. Do people hating you matters to you? And then whatever you say, he had a script, right? Okay. Weizenbaum disclosed how he did it. There goes AI. These guys are crooks or something? What's going on here? In the 80s, AI had a very bad name because of certain people. They were hiding. Same thing is happening. Okay? All right, skip all the videos. This is what we're doing in the AI lab at Bradley. I have some videos. Okay? So actually our students do go to the, I cannot see the picture very well, but go to the next one. Just play once, 2 seconds, 3 seconds of this. Oh, play that one. This is a joint project with the Department of Education. Look at these robots. She's trying to teach the concept of personal space. The guy went too close. Sorry, can you back up? Children with autism watch this and hopefully they learn what personal space means. Because they have trouble interacting with humans. Now, you watched Sophia. You watch this. What's the difference? The good thing about Sophia is you cannot see it in the video, but she can manipulate her face. At the same point, she says, "Oh, I'm sad," she does like this. Our robots cannot do that. But that's not the point. In terms of natural language, I could fool you and say, look, we have passing the Turing test. Those guys, look how they talk. If I tell you how we did it, not really, you know, not really. Okay. All right. Okay. Let's go a little bit faster. So this is my definition of AI. What's AI? It's not the hype. It's not androids. Here's, do the whole diagram. The AI is solving problems that are in the MP class, like the traveling salesman. It's a problem that cannot be computed, as far as we know at this point, in polynomial time. If you have one, I will not explain what it is, you can go online and check it. Traveling sales problem, go and watch the movie, Netflix. 2012 movie, The Traveling Salesman. Right? It's a must watch for these guys in the class. Okay? Famous problem. We know how to do it. We can build a Turing machine for it. But it's too slow. Nobody can do it fast in real time. AI steps in. Halting problem. Halting problem. Can you build a Turing machine to detect if there are infinite loops in other Turing machines? Cannot be done. Different than the traveling salesman problem. Traveling salesman problem, we can solve it, but not in real time. Our solutions are too slow. Halting problem. You can prove mathematically that this is a non-Turing computable problem. It cannot be solved. Computers cannot do this. Don't even try. But AI will say, if I can do a heuristic, and 99% of the programs you fit in, I can do them, and flag some infinite loops, I'll take your product. So what's the difference? Heuristic is natural language. We don't know if we can do this algorithmically. That's why Siri looks terrible and funny sometimes. Ask Siri, what's your mother? Okay. Okay? I tried that. She actually said, I was born in 2012 or something. Right? Okay? But I asked the same question later. And she said, I don't have a mother, you are my closest friend, she told me. Okay, all right. Okay, natural language. Yeah, right. You can see Siri does not pass the Turing test. Come on. Right? Okay. All right. So that's what AI is. The difficult problems that we cannot do computationally or we do too slow. That's my definition of AI. I have it in my book. That's what I say AI is. Forget all these things, the hype. They show you the robots. That's AI, man. Come on. Next one. I should not have called it AI, but I have no influence in the 60s when Minsky and those guys had the conference. They called it AI. That's what I would have called it. All right. Go. This is, so I worked in this area. We'll skip that. This, I borrowed these slides from one of my collaborators in Caterpillar. Different areas of AI, different kinds of algorithms. I put in red my modification. Algorithms I worked on, the reds are something I invented, those algorithms. So I have some algorithms in machine learning. Okay? Go next one. Okay. Next question. There is no general program prover. you will always have the danger of faulty software. You cannot fix that. Second question, is there a general problem solver? In the 80s, they tried. They had a system called GPS. It might have been Stanford, I don't remember the guy. Right? They were trying to do it with logic, mathematicians. Impossible. You have to capture some guy in the University of Texas. He tried to capture nature, the whole world, with logical statements and rules and stuff. Combinatorial explosion. He worked 10 years, 20 years. He had a very complex logical foundation, right? Okay? Like physics, the theory of everything. I have the logic of everything. You can ask any question to the system, that's his goal, I'll answer it. You know, I know everything. Cannot be done. Combinatorial explosion, he failed, right? These days, Google actually is working on the same problem. You see the recurrent here? If you stay in the field long enough, you can see what they're doing. Right? I can see Sophia and I can see Eliza. Okay? Now Google, they have a big deal out of it. Go and search. AutoML, auto machine learning. What's their goal? Since building intelligent systems is so difficult, we want to automate the process. We want AI to build AI. That's it, that's their goal. Question, can AI build AI? Maybe. Maybe. They're trying to find the general problem solver. But if AI can build AI, that AI that is building the AI must have in it a general problem solver. So if I want to build a vacuum cleaner AI, I build it. If I want to build a coffee server AI at Starbucks, I build it. You know. But I have to use the same algorithm, right? I know how to build things, that thing. Is there such a thing? Maybe. Next one. I'll skip that. Quantum computing, I have a point. 10 years, 20 years from now, if quantum computing succeeds, brute force will not be a problem. We don't need to think hard and fast how to solve problems. You can solve everything, most everything, with brute force. Some things brute force means, okay, you have a set, right? Find the brown object. Is this brown, is this brown, is this brown? Go through an object. Oh yeah, I found the brown object. That's brute force, right? Brute force in quantum computing will be a viable technique. Things will change, right? But still, even quantum computing, because of the philosophy arguments, will have the same problem. She will be able to do things faster, right? But she will not be able to prove other programs are correct. She will not be able to do certain things. Okay, next one. Where are we? Machine learning is the machine learns itself, right? Okay, keep going. We can skip that, we're very short on time. I give you some examples. There is an algorithm called genetic programming. And if you go in the notes, I give you an example how to use it. This is a possible problem, general problem solver we are looking at. If the machine thinks with genetic programming, she will be able, right, to build AI machines, if that works. And we have done it, like Koza is in Stanford, he has done it for small problems. Bunch of objects. Don't teach the robot anything. The robot arm, like those students were doing, don't teach the robot arm anything, right? Okay? But tell him what the goal is by showing him, okay, these objects, look robot, these objects, when you're done, they should be stacked here. Those objects, when you're done, let's say they'll be stacked here, and here and here. The robot will watch, oh, okay, I got the algorithm. Pick, smaller, bigger, bigger, bigger. She will do it correctly. Can this be done? He has done it. For that example, he can start, the robot can learn. If you show him what to do, the robot can, or the arm in this case, he can do that. Can we generalize? Possible. So, general problem solve, AI building AI, possible. It can come. Kurzweil, you know the futurist Kurzweil, big money at Google. He's the futurist at Google. In late 90s, he was saying, questions later. I see he's thinking hard. Kurzweil was saying, by 2018, is that next year? We'll have the singularity. Singularity means we'll have the first machine that will pass the Turing test and will be more intelligent actually than humans. He was wrong, right? Now he's saying he moved it by 20 years. Like some politician would know, right? He moves things. he's a futurist. But he's saying we'll reach singularity by 2040 now. I agree with him, but the only difference we have is in the time. I'm thinking more like 100 years. I agree with him. AI building AI. All right, so keep going. So I'll skip all those examples. Skip everything. I have a slide what data science is. We'll skip that. It's a process. The hot buzzword is data science now, right? Oh, data science. There's nothing new in data science, really. All the components have been there since the 70s and 80s. The only difference is we have better hardware, and we have cloud computing, and we have faster machines, and deep learning. We can do neural networks. When I trained a neural network in the 80s, right, backpropagation, it would take me 3 days to train it. Now, in the lab, software, they can do it in 1 minute, with 30 seconds. The same problem, 30 seconds. Immediately, so very fast. These things changed, which means you revisit old problems and you do them now, you have better solutions, right? Because the infrastructure changed. And of course, we keep inventing in AI. I'm not saying there's nothing new. I'm saying deep learning is not really deep learning. Neural networks have been around, right? Okay. Data science, yeah, it's machine learning and AI and all these algorithms we collected in the 80s and 90s and 2000s. Okay? All right. Keep going. All right, then I have some Caterpillar projects, which I don't have time to do, right? I collected, I don't know, 5 or 6 projects we did. Okay? One project is the demand forecasting. Well, this is the medical project. In that project, my point here is Bradley has some outstanding students. Some outstanding students. Right? We have done stuff that, the medical thing, Caterpillar Wellness Program. What was the, they have a huge big data. Big fuzzy word. Okay, big data. Medical forecasting system. Predict, based on the medical of each Caterpillar employee, what is his risk for cardiovascular, diabetes, and lung cancer. Then they will intervene in the wellness program and tell him exercise more or something. That slide shows that there was a pre-existing Harvard model, an NIH model. And when we did our model, we gave to Caterpillar, that's a Caterpillar slide, they compared with existing Harvard and NIH models, and we were beating them, look there. We were beating them. So that's these guys here, and you guys, that's these guys. I mean, so what are we talking about? Probably students are, we have some very good students, right? Okay, go next one. Keep going. That's the project that won that demand forecasting international competition. Okay? And we have the trophy out there for LAS guys. That's the project that got the trophy. It was like Brunel, there were a bunch of universities. One of those competing. We're trying to forecast the demand at the dealerships for Caterpillar based on previous history. Data science, machine learning. Okay? That is the architecture with, not that. That diagram, it was so complexity, I have a slide that says, complexity is simplicity to the nth power. If you look at our system, every component in the system was simple. You have a neural network, you have a genetic algorithm, you have a statistical method called Crosstone's method, the statisticians. It's like having many experts. They do their thing, they recommend, they will build models on top to collect the recommendations, aggregate the recommendations, and the models were different, and they build and they build and build, and we predict. Okay? That's where the Epicurean approach that I started with goes. How I solve problems. Epicurean approach. I use all the models that I know. I don't know how many models I know, 50 or 60. If you look in the literature, maybe there are hundreds. I don't know everything, obviously. Nobody knows. But I use everything I know, I hit it with everything. Epicurean approach. And I don't judge who is better and keep him, one model, because what he misses, he will get. Okay? I cannot, my Epicurean approach, being Greek, I made that up, right? Is that. you cascade models like that. You use all of them. Right? Everything in moderation. Don't throw away anything. And you win if you do that. That's a good strategy. Okay? Why we can do this? I could not do this in the 80s. I had to choose which one to use in the 80s because machines were slow. I can do this now. Here with everything. Oh, because the hardware. Okay, Moore's law and stuff, that's important. It allows you to do stuff. Okay, keep going. Keep going. Gemstone project, I will skip that. I was going to describe the algorithm. There is many mathematical theorems in that algorithm. It's a two-tiered network, logistic network, suppliers, ports, ships go to the port to port, assembly places, dealers, through ports, through land. It's a fuzzy network, look like graph theory. Graph theory, right? You have a graph and you have the weights are fixed. The cost is fixed. Here the weights are fuzzy because how much you charge from the ship to here depends on the energy price and other things. So it changes. It's an interval. So it's not a graph. So there's a lot of math in this. But it's AI also. We have theorems and this, and we have convergent theorems, where if you do this back and forth, you converge and you find how to ship things and make profit. We have conflicting goals, Epicurean approach. Maximize profits, right? Minimize service time, how fast you get your stuff. Conflicting goals. How do you do this? How do you find the balance? Epicurean approach. Many recommendations, combine them, do stuff. Okay, keep going. Keep going, let's keep going. All right, we had a slide, say like a few words. She's doing a thesis on data science right now. And we don't have time for yours, I think that I see anxiety here. She's working in a different project in logistics. She's doing a data science project. Say a few words. She will finish her thesis in May. She will give a presentation around May. If you want to come and watch in May, she will be giving. Say a few words.
It's about prediction of rheumatoid arthritis. That's a disease related to the bones and stuff. And we had Dr. Masi who has given us the data set, so we'll be doing that. Basically, I collected the data sets from University of California Irvine Data Repository, the medical domain, and I built an ontology for all those. Like I built properties and the relations between them, and try to apply all the machine learning algorithms on them. And classify them, like which kind of property would have better impact when this kind of machine learning algorithm is applied. So that when a new data set comes in, so when you look at the properties of that data set, it falls into one of the categories of these, and you could directly go and apply this machine learning algorithm, which is more appropriate rather than searching each and every algorithm and checking for the accuracy. Yeah, and the last step would be even considering our data set and
we'll do the thing we're talking about. She will try to make, like, we want to gather some structure like that, right? To efficiently solve the problem. Go to the next slide. And keep going. Oh, yeah. We'll not go this. If somebody is a newbie, but you're excited, who said you're a civil engineering? Where's the civil engineer? Are you excited? I did not know you would be here. I could have some slides for you. If you're excited, send us email, go to the last slide, and we'll tell you where to load, even if you know nothing, how to learn something. Okay? Go to my book, go to online, go to these books, online reference, websites, watch these videos. Coursera, you know Coursera, right? There are free courses, online courses all over the place. You can learn, don't worry. You don't have to be a CS guy to be able to apply that. And remember, Google project, AutoML. Right now, the MS, these guys want to make big money. No, they like AI and data science, that's why they came. But some of our graduates in that field, 6 figures. Yeah, 24-year-old. Last year, in the logistics project, 6 figures. 24-year-old. Okay. 10 years from now, the Google project wants to kill that. You will not be finding in our field 6 figures because AI will be building AI, right? Part of Google's motivation is in the whole United States, there is only 10,000 people that are very competent at doing this stuff. and Google is fighting Facebook, and Facebook is fighting this other guy, and then they have to give high money into these guys, right? But 10, 20 years, they're too young, they have to retrain. The machines will be doing what we're doing here, really. Okay? So my projection is, yes, AI will be building AI. And I will not go to the society discussion now. Society, impact, you guys can talk. It's possible. It's coming. 20 years, or 50 years, or 100 years, I cannot tell you, it's coming.
We're over time, but maybe 2 or 3 questions?
Okay. So I just,
You take the question.
okay, questions? Yeah.
Could we go back to the slide that looked for, was it when you introduced the genetic programming model and
Okay.
it was to detect the error with 1 over the square root of
Yeah, yeah, yeah.
errors?
Can you find that? Keep going.
Yeah, it's gonna be, because we skipped some stuff.
I'll
but
do this when you find it.
It was only a few minutes, that could
here.
have been it, okay, no,
No, one before?
there,
There.
okay. Who detects the errors? And how is that to be computed? Okay, how does that input go?
Right, okay. So in my
Because in all the
example,
science fiction, like in
Yeah, I know,
2001 Space
I know.
Odyssey,
I know.
the computer
Yeah,
doesn't
exactly.
recognize what we, the audience, would constitute an error.
So, state of the art is you have to give him the correct representation, like they were trying to do when they saw the things. If you give me the wrong input to the learning system, I will fail. What I'm trying to do here, area equals pi r squared. Do I do pi r squared? Yeah, pi r squared. I'm trying to learn this. So you have to give me data. You give me, so I take some circles, right? I calculate the radius, measure. Okay? Let's say the circles I made are also strings. I spread them out like this into rectangles. I take my ruler. Okay, what's the area? Very easy for them. I should have done this on the table too. Here's the area. Then you go and you make this table. That radius, that area. That's the input. Now, genetic programming tries to find the formula. Because the program here will be read an R, output an A. What's the middle code? A equals some formula, right? Very simple case I do. Find the formula. Okay. The machine learning, nobody tells her, oh, you know, Euclid did that. No, she has to learn from the data. How does she find the formula now? She generates random formulas, as in the previous slide, trees. Random formulas. And if you look at those are called expression trees. If you look at the first formula might be 3 plus 2r. And the other formula is whatever, r cubed minus 1. Genetic programming is generate a lot of expressions like that. And then you have what is called, like in genetic algorithms. You cross them over, like DNAs, they have children, right? Okay, you cut part of this, you create new trees, okay? And you have a reproduction of the fetus. Your question is, how do you judge who is the fetus tree? What's the error? I want the tree with the smallest error. What's the error? Okay, so if my tree, the formula is 3 plus r, and the radius is 1, the formula would say output 4. But it should be 3.14. I gave him what it should be. That's supervised learning. I told the system what it should be 3.14. Then, when she generates a formula, she can find the error. That's how she finds the error. Supervised learning. If you don't tell him what the output should be, you cannot find the Euclid's. You cannot find. You have to give him examples, and the correct examples in the right format.
Well, I'm trying to cogitate whether or not, with rapidly changing environments in which any system will operate and try to measure error, whether or not the formula for determining the error is going to alter over time as well.
Well, you have a
That
very good
happens
point
in
there.
real
Yeah, I know.
genetics.
That's a very excellent idea, right?
Yeah.
Yeah. Is the formula constant over time?
Yeah.
in some stochastic systems, the formula changes, right? Okay, okay. If the form, I have not thought of that. How do you do machine learning over time? Okay, temporal machine learning. I don't know, maybe you do it with the data you have now, and you learn something, and you're using it. As more data comes in, all right, you use the new data and the old data, you learn all the time. You learn all the time. So with the data you have a formula. Instead of pi r squared, you found r squared. Maybe you're using it. Maybe your data was not good enough, right? You're using, but new data is coming in. That's what you're saying? You don't have the correct formula. Or the formula changed because your data was coming in 3.1. You had 1 digit accuracy. And now you're more accurate, you have better sensors, and you say now it's 314. And then you say it's 31472, and you're becoming better in collecting data, right? So the formula will change, okay? So you learn, you use more stuff. As you're using, relearn, it changed, compare, or it's better because the new data might be terrible. Compare, swap, keep doing in a loop. Yeah. Do you have fast enough machines, though, to do that? We're getting, imagine again, 10 years quantum computing, come on, that's not a problem.
Chris, how about one more question maybe from, from a student?
Yeah.
If they're willing.
So if we were to somehow find a way to represent everything in the world as a vector, as something that can be easily manipulated by like a Turing machine, what would be the next hurdle?
Okay, so the first step is the representation. Suppose we solve this. All right. The next step is the following. Right now, the machines do not know what to learn. You have to tell the machine, here is my data, learn the area of the circle as a function of the radius. I gave her the goal. AI, if it's AI, the human will be out of the loop. The next step is get the human out of the loop. Don't tell the machines what to learn, right? The AI will learn what she needs to learn to survive, like we do. When I'm born, I don't know what to learn. I just fiddle around, I make mistakes, and I adjust. AI completes AI and learns itself. She will create, the next steps, we cannot do this right now. She will create her own goals. I need to learn this, because every time I go, I hit another robot. I need to learn how to navigate or whatever it is to learn. Once AI learns how to learn, we're in trouble. Can this next step be done? Yes, it could be autonomous thinking machines. We can build like error functions.
Yeah.
Error functions, right? And if something is not, when I hit another robot, I realize it's not good. So what should I do? Oh, I don't have a sensor here. She will go to the lab. And the assembly line, the machine will be studying sensors over here because they need it. And once this is done, she will figure out, why I hit the other robot? Because, Asimov's 3 laws, robotics laws, right? Anyway, Asimov is a fiction writer. It's colloquialism. But one of the laws says, when you build an AI robot, one of the first laws is you should not harm a human. I'm watching Dark Matter these days on TV. Anybody saw Dark Matter, the science fiction movie? 3 years in a row running. They have this android. She controls the whole ship, spaceship, by thought process, right? And when something happens, right, her first law is not to hurt a human. She goes out of her way, hurting herself, it's a female, not to hurt a human. And then what happens in an episode, 2 humans fight each other to kill each other, and she does not know what to do. Because should I let them both hurt? What do I do now? My rule says I don't hurt a human, Okay? But when this happens, if she figures that you're on the way, right? Don't hurt a human What does that mean? That's a colloquialism. How can I program robot? What does harm mean? This is a fuzzy term. How do you program that? Pushing you is the harm? Can she push you? Yeah, can she scoop you down? Can she, what does harm mean? Once they do AI as AI, we're in trouble. Right? Because they can throw it away so she can do the thing.
Thank you, Chris. Join me up here. No, that's okay. So, as Dean of the College, on behalf of the faculty, staff, and students, I want to thank you for your presentation and present you with a small token of our gratitude. I want to thank Pat Campbell for organizing this event. I want to thank the student assistants. I greatly appreciate your attendance here today and your attentiveness, and wish you well for the remainder of the semester. Thank you so much for joining us, and enjoy the refreshments. Good night.